Good afternoon, students. So hope you are very well and you are doing very good practice. So welcome to this rapid review series. Today's lecture number 14 that we have chapter is atoms and nuclei. So we are discussing the modern physics. Yesterday we discussed the dual nature of matter and radiation. We solved the questions from the photoelectric effect and de Broglie wavelength. Today we will be discussing these two chapters. These two small chapters we have atoms and nuclei. Atoms part we already discussed in the chemistry and nuclei part we will be discussing today. So let's discuss what are the things that we are going to discuss in this. First one is Bohr model of atom. The maximum number of questions is asked from the Bohr model of atom, and second is line spectrum of the hydrogen atom. So line spectrum we have the Lyman series, Balmer series, like that we have Paskins, Pfund and Humphrey. That bracket Pfund, those Lyman series, Balmer series, those are what we define line spectrum of the hydrogen atom. Bohr model of the atom we will be discussing in this three postulates of the Bohr. Next we have nuclei. In the nuclei, what are the chapters that what are the topics that we should revise? Nuclear size, nuclear force, mass defect and binding energy. That these are the topics that we should be focusing on this nuclei. So let's see the weightage wise over the years how many questions we can expect on an average. The number of questions from the atoms and nuclei in the NEET 2020 starting from 2014 to 2023. So we can expect this atoms is there, nuclei is there, and here one questions from the atoms over the year continuously they're asking. Second is some questions 2, 3, 2, 1, 2, 1, 2, 1 question asked. They're asking from the nuclei. So on average one question from the nuclei and one question from the atoms we can expect from these two topics. The first thing that let's start with our journey is that Rutherford alpha particle experiment. We all know what Rutherford do. So he took one gold foil and he took one zinc sulfide material over here and he placed one source of alpha particle streaming material over here. This narrow beam of fast moving alpha particles is strike given this gold foil. What are the different observations he has made? What are the different observations here made in that? Most of the alpha particles are passing without deviation. So most of the alpha particles are passing without deviation in this case. So most of the alpha particles will be passing without deviation, that is 0 degree. Some of the alpha particle, very less alpha particle are passing through some deviation by 1 degree, 2 degree, like that 180 degree. Very few are passing by 180 degree. So this conclusion, this concludes that most of the space in the atom is vacant. So what are the conclusion we have in Rutherford? So if we talk about the size of the atom is 10 to the power minus 10 meter. If you talk about the size of the nucleus is 10 to the power minus 15 meter. 10 to the power minus 10, this is 10 to the power minus 15 meter. The entire positive charge is situated, that is concentrated near its center, and that is what we define nucleus in a very tiny region. And what is size of the nucleus? We have 10 to the power minus 15. What is size of the atom? 10 to the power minus 10. If cricket ground is the cricket stadium is the atom, then cricket ball will be nucleus. That much small nucleus is as compared to atom. That is, this is the size of the atom and this will be size of the nucleus we have. Now the negatively charged electrons revolve around the nucleus in different orbits, just like planets revolve around the sun. The negatively charged electrons revolve around the in different orbits around the nucleus. The total positive charge on the given atom is inside the nucleus is equal to total negative charge, that is total electrons, negative charge on the electrons that is surrounding it. So this we are coming to conclusion over here. Next, whenever the electrons are revolving around the nucleus, the force is required because it is revolving in a circular path, just like the planets do revolving around the sun. So in that circular path, if any electron is revolving, that requires the centripetal force. And who will give that centripetal force? The centripetal force is given by the Coulombic force of attraction between the nucleus and the electrons, right? Nucleus and the electrons. So these are the observation we have. So what are the observation? Size of the nucleus. What are the observation? Size of the atom. What are the observation? That all the particles are all the electrons are revolving in a circular path. Now what are the drawbacks we have for the Rutherford model? What are the drawbacks we have? This model failed to explain the discrete wavelength in hydrogen spectra. So we got when there was hydrogen spectra, like we got some particular lines or some particular dark lines in case of the hydrogen spectra. So that is not explained by this Rutherford. That is becoming drawback of this. When the electron is revolving around a circular path, electron is moving in a circular path. As it is moving in a circular path, it is accelerated. If any charged particle is accelerated, it will emit electromagnetic radiation according to Maxwell's theory of electromagnetic radiation. If any charged particle is accelerated, it will emit the electromagnetic radiation, and when it will emit the electromagnetic radiation, it is emitting the energy, and when it is emitting the energy, we call it as, it will lose some part of the energy. And if it is losing some part of the energy in form of electromagnetic wave, so finally its energy should decrease, and once its energy will decrease, it should finally collapse into nucleus, but that doesn't happen. So this is what Rutherford could not explain the stability of the atom. The wavelength of the radiation should be related to the frequency of the revolution, thus the electrons should emit the radiation continuously varying wavelength. So these are the drawbacks we have. Then there comes Rutherford. So what is Then there comes Rutherford. That is, there comes a Bohr model of hydrogen atom. The first one is three postulate he gave. The postulate number 1. So postulate number 1 says that whenever electrons revolve around the nucleus, it will revolve in certain orbits where it does not lose any form of energy. Those orbits is also what we define stationary states of the atom, in which we define that if atom is there, this will be K cell, this will be L cell, this will be M cell, and this will be N cell. So electron will revolve in certain definite stable orbits without emitting radiate energy, without emitting any electromagnetic radiation. Electrons will be revolving in only certain orbits. That is a postulate number 1. And he, in this postulate number 2, he also mentioned that what are the energy states that is allowed. So this one is K, L, M, N. What are the energy states that is allowed? He mentioned any energy state that is allowed in which angular momentum of the electrons should be given by mvr, should be given by nh by 2 pi. What is n value? N value is 1, 2, 3, 4, 5. So whenever the only certain stationary states are allowed in which the angular momentum should be nh by 2 pi, means for the first one it will be h by 2 pi, for so n equals to 1, so this will be h by 2 pi. For n equals to 2, this is 2h by 2 pi. So like that, n equals to 3, this is 3h by 2 pi. So only certain energy states are allowed in which the angular momentum is given by nh by 2 pi, where n is the integer starting from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these states are also defined as what is state? Energy states. And these states are stable energy states in which if the electrons revolve, it does not emit any electromagnetic radiation. So net loss of energy will be 0 and electron will continue revolving around. Like this explains the little bit stability of the atom. So that is the Bohr model. So this is second postulate we have. What is the third postulate? Third postulate is very simple. So for example, around the nucleus there are certain orbits. So this one is K shell, this one is L shell, and this one is M shell. So if the electron is revolving in certain orbits, and suppose if it absorbing energy, so these are the energy levels. In energy will be fixed at this particular point, this particular point, this particular shell, this particular shell, this particular shell, energy will be fixed. When the electron is absorbing energy, it will move to here, or it can move to here, depending on the situation. So for example, let's say we know for the ground state, this is minus 13.6 electronic volt, and this is minus 3.4 electronic volt, and this is minus 1.51 electronic volt. So here, if the electron is taking the energy and in form of the light, suppose if it's taking the energy, electron will jump from the lower energy state to higher energy state. On the other side, what will happen? If the electron, so in this case, it will absorb, when the electron is jumping from this point to this point, it will absorb the energy. If the electron is jumping from the higher energy state to lower energy state, it will release the energy, and when it releases energy, it will release energy in form of the wavelength, in form of the light of photons, it will release energy. So whatever the energy in form of the light, either it is absorbing or releasing, depending. If it is coming from higher energy state to lower energy state, it will emit energy. If it is going from lower to higher, it will absorb energy, and that energy is given by delta E. What is delta E? Hc by lambda, or I can write here H into mu is equals to E initial minus E final. Okay, so this is the differential energy, and always no need to worry about this. You take the magnitude only, E initial minus E final, you take the magnitude, your problem will be solved over here. So this is Hc by lambda that we are getting over here. Right. So this energy will be released or absorbed depending on the electron is moving from here, energy will be absorbed, electron is moving from here, energy will be released. And different states will have different energies. So this one is having minus 13.6, minus 3.4, minus 1.51. These are the energy levels we have. This is the Bohr's third postulate. So if we talk about the Bohr model is defined for hydrogen-like elements. So first one is hydrogen itself, that is hydrogen atom. Second is He plus here Z equals to 1, He plus Z equals to 2. Next one is Li2 plus. What is Li2 plus? Z equals to 3. Next we have Be3 plus. So Z equals to 4. In this all case, only one electron is species, we call it as. All this will be having one electron. No, number of protons might differ because that is inside the nucleus, but electrons will be same, that is 1. So for this one, number of electrons will be same, that is 1. And this Bohr model is only defined for this kind of species. We have only one species, we call it as hydrogen-like species. We are having single electron, like number of electrons is 1. So what is actually happening if the electron is revolving in this particular manner? So if the electron is rolling in this particular manner, electron is rolling around this. Inside this nucleus we have Z into E. What has happened? This one is electron and this one is proton. This is positive or this one is negative charge. There will be Coulombic force of attraction between them. And what is Coulombic force of attraction? That is KZE multiplied by E divided by R square is equals to, from here we'll be solving this, that is mv square divided by R. What is R here? R is the radius. Okay, this R will be radius. So suppose if I writing this, R will be radius. So solving this particular equation, second equation that we have, angular momentum is given by mvr is equals to nh by 2 pi. What is n here? N equals to 1, 2, 3. So I am not going to do derivation part. This will take a lot of time. I will just calculate what are the things that we should keep in mind. So after solving this equation 1 and equation 2, we can come to some conclusion that radius of the first orbit, radius of the nth orbit, radius of the nth orbit, we can write here Rn. What is Rn? This is a0 into n square by z. Okay, radius of the nth orbit. Second is velocity in nth orbit, velocity of the electron in nth orbit. So this one we can write here, velocity of the electron in nth orbit, that is Vn equals to, what is a0? A0 value is 52, 0.53 angstrom. Okay, so this will be 0.53 angstrom. We also call it as, this one is also called it as Bohr radius. So this will be also we call it as Bohr radius. Velocity in this nth orbit is given by c by 137 into z by n. Z is atomic number, n is the principal quantum number. So this n is the principal quantum number, that is number of the cell, K cell, L cell, M cell, M cell, N cell. Putting the n, so this, if we solve this particular term, we'll be getting c, what is speed of the light, 3 by 137 into z by n. So this is 2.2 into 10 to the power 6 z by n. These are the, we have speed of light in nth orbit. Second, if we talk about the third one, that is the kinetic energy. What is kinetic energy? We have half mv square. So half mv square. So v is proportional to what? So here we can write, from this particular term we can write what is v is proportional to, as the v is proportional to z by n, right? V is proportional to z by n, so v square will be proportional to z square by n square. So kinetic energy from here I can write, that is, I am directly writing the formula, that is 13.6 z square divided by n square. Kinetic energy in nth orbit, kinetic energy in nth orbit is z is 13.6 z square by n square. And what is total energy? If we have, the total energy is minus of kinetic energy is equals to minus of potential energy divided by 2, sorry, plus of potential energy divided by 2. So this is that relation that we should keep in mind. So what is total energy from here? Total energy is minus 13.6 z square divided by n square. Next, if I ask you what is time period? What is time period? Time period is given by 2 pi r divided by v. So r is proportional to n square by z. And what is the velocity? The velocity is given by z by n. So time period is given by t is proportional to r by v. So this t is proportional to r by v, we can write here t is proportional to n square by z divided by z by n. So what is this? N will go upside. So t is proportional to n cube divided by z square. So this is the time period we have. Next, if they're asking frequency relations, what is frequency? The frequency is 1 by time period. So from here I can write here frequency is 1 by time period. Frequency is 1 by time period. So frequency is proportional to z square by n cube, right? So next, if we talk about the current, what is current? If the electron is revolving in a certain orbits, because of this electron there is current over here. So current is given by I. What is I? Q multiplied by F. Okay, where F is a frequency, here I is equal to E multiplied by F. So I is proportional to frequency, and what is frequency is proportional to Z cube by N cube. So current is proportional to Z cube by N cube. Clear? Current is proportional to Z cube by N cube. Next we have magnetic field. So what is magnetic field? Mu naught I divided by 2R. Mu naught I divided by 2R because of this current carrying wire. So B is proportional to I by R. Right? B is proportional to I by R. So B is proportional to I by R. This is proportional to B. I is proportional to what? Z cube by N, Z square by N cube divided by this R. N square by Z. So this is what we are getting. Z cube divided by N cube power 5. This is the magnetic field that we are getting. So these are the quantities we have that should keep in mind. They will be asking the radius ratio. They will be asking the ratio of the different quantities from the different orbits of the different elements. It can be Z value and N value. We have to substitute that set. Okay. So next we have. So these are the just summary point of this. R is proportional to N square by Z. R is proportional to 1 by M. Okay. Inversely proportional to mass. V is proportional to Z by N. V is proportional to M k power 0. E is proportional to Z square by N square. E is proportional to mass. This is the Bohr radius. That is the smallest radius. This will be Bohr radius we have. This one is the velocity in the first orbit, that is C by 137 value is 2.2 in 10 power 6. We have written over here. The kinetic energy value, total energy value is minus 13.6 for the hydrogen atom, that is Z square divided by N square. For the ground state energy, we will be having this. Kinetic energy is equal to potential energy. Kinetic energy is equal to total energy, and that is potential energy is equal to double of total energy that we have. And this is in nth orbit, that is T is proportional to what? N cube divided by Z square. So these are the things that we have. So next one we define, that is line spectrum of this. So before this, what are the things I want you to remember is that N equals to 1 for hydrogen atom. We should remember this hydrogen atom, N equals to 1. So N equals to 1. What is energy? Minus 13.6 electronic volt. N equals to 2. What is energy? Minus 3.4 electronic volt. N equals to 3. What is energy? Minus 1.51 electronic volt. Minus 1.51 electronic volt. N equals to 4. What is energy? Minus 0.85 electronic volt. So these are the energy levels we have for the hydrogen atoms. If they are given for the helium multiplied by Z square, so energy, total energy is given by minus 13.6 Z square by N square. I have derived for Z equals to 1, that is hydrogen atom. If they are asking for the helium atom, Z equals to 2. If they are asking for lithium atom, Z equals to 3. If they are asking for beryllium atom, Z equals to 4. Is that clear? So this will be N will keep on reducing. The total energy is inversely proportional to minus of 1 by N square. We'll be discussing this one. So let's coming back to here. That is the, what is that? Line spectrum of the hydrogen atoms. No matter from where you are coming, if your destination is N equals to 1, if you are coming from 2 to 1, if you are coming from 3 to 1, if you are coming from 4 to 1, if you are coming from 5 to 1, if you are coming from 6 to 1, if you are coming from infinity to 1, no matter from where you are coming, if your destination is 1, you will be called as under Lyman series. Second, if you talk about the Balmer series, if you are coming from 3 to 2, 4 to 2, 5 to 2, 6 to 2, next with infinity 2, you will be under Balmer series. Next, this one, Pascal series. No matter from where you are coming, you should be coming from 3 to 2, 4 to 2, 5 to 2, 6 to 2, so sorry, 6 to 3. So this will be called as Pascal, and what is bracket? The destination is 4, and what is P fund? The destination is 5. So in this case, first, this is when we are jumping from N equals to 2 to N equals to 1. That will be called as first line of Lyman series. If you are jumping from, if the electron is jumping from N equals to 3 to N equals to 2, N equals to 1, this will be called as second line of Lyman series. If it is jumping from 4 to 1, that is will be third line of Lyman series. If it is jumping from infinity to 1, that is last line of Lyman series, and we also call it as, this line is series limit, and this series limit, this will give lambda value will be minimum. In this case, the lambda value will be minimum, and in this case, that is the first line, this will lambda value will be maximum. Okay, lambda value will be maximum. Suppose this is, that is N equals to 2, 3 to N equals to 2, if it is jumping, that is the first line of Balmer series, and here we will be defining, this one will be first line of Balmer series, this will be defined as, first line of Balmer series, and here lambda value will be maximum for this Balmer series, and this series limit, that is when the jumping from N equals to infinity to N equals to 2, this is the last line of Balmer series, and we also call it as, this will be series limit. Okay, series limit. And this particular things we can relate by one particular expression. What is that? So this, when it is jumping from, So here we define 1 by lambda, that is the wave number, so this will be wave number, that is 1 by lambda, and that is given by r multiplied by 1 by, what is that, 1 by n final square minus 1 by n initial square. Okay, n final square minus 1 by n initial square. In terms of the energy, if you write this one, so this will be 1 by n initial square. So this particular term, that is n final is equals to 1, n initial is 2, 3, 4. This will give us Lyman series. Okay, this will give us Lyman series. And in terms of the energy, if you write this, so this will be hc by lambda is equals to delta E, and that is given by 13.6 z square into 1 by n final square minus 1 by n initial square. Okay, final square minus 1 by n initial square. Now this is what we define, this particular term, this is what we define Rydberg constant. What is Rydberg constant? R value 1.097 into 10 to the power 7, or I can write approximately 1.1 into 10 to the power 7 per meter. That is Rydberg constant that we will be taking. And finally is where it is coming from, where to where it is coming, and what is n initial, from where it is jumping. N is initial to n final, right? So this will emit, so this all will be called as Lyman series, that is when it is jumping to n equals to 1. When it is jumping to n equals to 2, Balmer. When it is jumping n equals to 3, Pascal, and this will be bracket, and this will be Bfund, and so on. So here we have, that is n equals to electron jump from where to where. So electron jump from, that is electron jump from n equals to 2, 3, 4. Electron jump to n equals to 1. We call it as which limit? This one is what we define, Lyman. And what is series limit? This is the smallest wavelength. When this will be, that is when the infinity to it is jumping from n equals to 1. And what about this one? When it jumping from n equals to 2 to n equals to 1, right? This will fall under this UV rays. Okay, remember this. This falls under the visible rays, that Balmer series. This will fall under near infrared. This will fall under mid infrared, and this will fall under infrared, far infrared. Okay, so here electron destination is n equals to 1, n equals to 2, n equals to 3, n equals to 4, n equals to 5. What is wavelength relation? We'll be writing this 1 by lambda is equals to r times of final is 1, so 1 by 1 square minus 1 by n square, right? Second, so 1 by lambda is equals to r times of, what is final? I told you n final square minus n initial square. So 1 by lambda r 1 by 2 square minus 1 by n square. N value is 3, 2, 4. 1 by lambda here, r multiplied by this 1 by 3 square minus 1 by n square. So 1 by lambda is equals to r times of this 1 by 4 square minus 1 by n square. Last one, 1 by lambda is equals to r multiplied by this jumping to where n equals to 5, 1 by 5 square minus 1 by n square. So these are the wavelengths or wavelength relation we have for the different series that we have on this. It only depends from where you are coming and where you are jumping to, right? So let's solve some of the questions from it. Atoms are electrically neutral as they contain equal number of positive charge, equal number of negative charge. Yes, statement is correct. Atoms of each element are stable and emit their characteristic spectrums. Again, this particular question, if we talk about this stability with respect to atom only, some atoms are unstable, like radioactive elements, those are unstable. So this particular question, yes, this one is correct, they emit their characteristic spectrum. So this part of the question is wrong. So I will say statement 1 is correct and statement 2 is incorrect over here. Okay, the ground state energy of hydrogen atom is minus 13.6 electronic volt. So this is n equals to 1. What is energy? Minus 13.6 electronic volt. Energy needed to ionize the hydrogen atom from its second excited state. What is second excited state? So this n equals to 1, n equals to 2. This is the first excited state, right? This one, n equals to 3. This will be called as second excited state. So excited state is just minus one of the energy state. These are the energy state. This is the first energy state or ground state, but this one is the second energy state and first excited state. This will be third energy state but second excited state. What is energy? If this energy is minus 13.6, I told you this will be minus 3.4 electronic volt, and this one is minus 1.5 electronic volt. One electron is sitting over here. What is ionization energy? Ionization energy is the energy required to give this much electron so that it reaches the infinity. When it reaches the infinity, what is energy at infinity? 0. What is difference in the energy? Minus 1.51. This one is 0. What is difference in this energy? That we have 1.51 electronic volt. That is what ionization energy we have for this excited state of the electron. If the electron is sitting over here, then what is ionization? 13.6. Electron is sitting over here, then ionization energy will be 3.4. But electron is sitting in this particular manner, that is second excited state, that is minus 1.51. So energy required is 1.51. Moving to next question over here. The total energy of electron, I told you what is total energy? Minus of kinetic energy is equals to potential energy divided by 2. So what is kinetic energy? If this one is minus, then kinetic energy will be plus. So kinetic energy will be plus, and double of this will be potential energy. So this will be kinetic energy will be plus 3.4 electronic volt and potential energy is minus 6.8 electronic volt. So moving to next question over here. The angular momentum of electron in orbit. So angular momentum L is given by mvr should be equals to nh divided by 2 pi. What is n here? Number of principal quantum number, that is number of orbits. So nh by 2 pi, the value is given by how much? 1.5 h by pi. 1.5 h by pi. Pi or pi cancel. So this n by 2 is equals to 1.5. So what is n? 1.5 multiplied by 2. How much you got? That one is 3. Okay. N equal is 3. What they are asking? Angular momentum they are asking now. This one, the energy in the same orbit is given by. So what is energy? Total energy is given by minus 13.6 z square divided by n square. But what is the value of the z? The value of the z we have hydrogen atom. Okay. 1. So minus 13.6 divided by n value is 3 square. So this is minus 13.6 divided by 9. So this we are getting how much? Minus 1.5 electronic volt. Okay, minus 1.5 electronic volt. Let r1 be the radius. Let r1 be the radius of the second stationary orbit of, and r2 be the radius of this fourth stationary orbit of electron in Bohr's model. The ratio of this. Okay, r1 be the radius of the second stationary state of the stationary orbit, and r2 be the radius of the fourth stationary state of the electron in Bohr's model. Bohr's model means hydrogen. So what is radius? Radius is proportional to what? N square by z. They have not mentioned anything about different elements. So z value is same. Consider both is for the only hydrogen. So z value is 1 for both. So r is proportional to what? N square. That's it. Okay. So first one is n equals to 2, and second case n equals to how much? 4th. N equals to 4. That is 4th. So from here I can write that r1 by r2 is equals to n1 by n2 ka whole square. So what is n1 by n2 we have? So this is 2 by 4 ka whole square. 1 by 2, that is 1 by 4. Answer is 0.25. Okay, 0.25. So moving to next question. Consider third orbit of He plus. So this is, let's say, He plus, n equals to 1, n equals to 2, and n equals to 3. So what is z value? 2, n value 3. Okay, third He plus. Using non-relativistic approach. Non-relativistic approach means we are not following the relativity theory, that is velocity mass will change. In that case we are not using this with the speed. The speed of the electron in the orbit will be given by, what is speed of the electron we have? V is equals to 2.2 into 10 to the power 6 z by n, right? That's it. Putting the value 2.2 into 10 to the power 6, what is z value? 2, and what is n value? 3. So this will be, we are getting how much? 2.2 into 10 to the power 6 divided by 2 by 3. So this approximately, that we are getting how much? 4.4 into 10 to the power 6 divided by 3. So approximately we are getting 1.46 into 10 to the power 6 meter per second. Moving to next question. The spectral series which corresponding to electronic transition from n2 is equals to 5 to n1 equals to 4. What is final destination? The destination is 4. Lyman n equals to 1, Balmer n equals to 2, bracket, so Balmer P fund they are asking. So spectral series which corresponding to, here we have, so this particular case, that is Lyman n equals to 1, Balmer n equals to 2, Pascal n equals to 3, bracket, they are jumping to n equals to 4, and P fund n equals to 5. So what is the question they have mentioned over here? As per the given question, n equals to 4. So this one is what? Bracket series. So this is n equals to 1, n equals to 2, and this is n equals to 5, and this one is n equals to 4. That is final distance, and should be 4. Hydrogen spectrum, the shortest wavelength in the Balmer series is lambda. I told you, suppose if this is Balmer series, starting from this n equals to 2, n equals to 3, and this is n equals to 4, this side n equals to 5, n equals to 6, and last one let's say n equals to infinity. So what they are asking, shortest wavelength is lambda. The shortest wavelength in the Balmer series is lambda. The shortest wavelength in the bracket series will be given by. So what is bracket series? So first, when we take the shortest wavelength, when it is coming from infinity to, when it is jumping from where to where, that is when it is jumping from, when the electron is jumping from infinity to 2, this will give shortest wavelength in Balmer. Okay, shortest wavelength in Balmer. So how can we calculate this? So for Balmer, I will be writing this lambda minimum, in this case r multiplied by 1 by final is 2 square minus 1 by infinity square. Okay, next, the shortest wavelength in the bracket series. What is bracket series? N equals to 2, n equals to 3, that is n equals to 4. This one we have to take it as bracket series, again infinity to 4. So in this case, bracket series, the shortest wavelength is given by lambda minimum, in this case is equals to r multiplied by 1 by 4 square minus 1 by infinity square. So this we are getting, so sorry, this is 1 by lambda, this also 1 by lambda. So from here we got, this is 1 by 4. So what is lambda in Balmer? The lambda in Balmer that we got 4 by r. And what is lambda in bracket? The lambda in bracket we got, this is 0, 1 by 16, this will be 16 by r. What they are asking? Ratio. The shortest value in the bracket series is how much? So this one is 4 by r and that one is 6 by r. So answer will be 4 lambda. Because this is lambda, that will be 4 lambda. Clear? The wavelength of Lyman series is of hydrogen appears in visible ultraviolet region. If it is Lyman, ultraviolet, visible means Balmer, and this one, far infrared, this one is P fund, and this is bracket. This will be bracket. So this one is UV region. Okay. So ratio of the wavelengths of the last line of the Balmer series and the last line of the Lyman series. Last line of the Balmer series and last line of the Lyman series. So just now we saw the last line of Balmer. What is last line of Balmer? N equals to infinity to n equals to 2. And last line of Lyman, that is n equals to infinity to n equals to 1. So from here, that is 1 by lambda 1 is equals to r divided by 1 by 2 square minus 1 by infinity square. In this case, 1 by lambda 2, it is jumping from where? And 1 by 1 square minus 1 by infinity square. So from here I can write here lambda 1 is equals to r 4 by r. Okay, this will be 4 by r. And what about this one? The lambda 2, what is lambda 2? This will be exactly equals to r, 1 by r. This is 1 by r. That's it. So what is the ratio? The ratio is 4. Clear? Lambda 1 by lambda 2 ratio is 4. This is 4 by r, that is 1 by r. So this is the last line when it's jumping from n equals to infinity to n equals to 1. When it's jumping from shortest wavelength we want, this will give us shortest wavelength. Longest wavelength will give, that is the first line when it's jumping from n equals to 3 to n equals to 2. In case of the Balmer, that will be getting the shortest wavelength in case of n equals to longest wavelength in case of n equals to 3 to n equals to 2. This will give us first line of the Balmer. And here Lyman, n equals to 2 to n equals to 1, this will give us first line of the Lyman. Clear? An electron in hydrogen atom jumps from third orbit to second orbit. It emits a photon of wavelength lambda. So it is jumping from third orbit. that is n equals to 3 to n equals to 2. When it's jumping from n equals to 3 to n equals to 2, it emits a photon of wavelength lambda, right? Electron is jumping from here to here. When it jumps from fourth orbit to third orbit, corresponding wavelength of the photon will be given by. So here that is n equals to 4 to n equals to 3. Just simple ratio that we have to calculate. What is formula we are having? That is 1 by lambda. What is 1 by lambda? R times of this, jumping from where to where? Final we have to write first, that is 1 by 2 square minus 1 by 3 square. So 1 by lambda in this case is given by R divided by this 1 by 4 minus 1 by 9, 9 minus 4, that is 5 by 36. We are getting this. So what is lambda in this case? The lambda in this case we are getting here 36 by 5R. I hope this is clear. Now in the second case, electron is jumping from here to here. Okay, electron is jumping from here to, that is 4 to 3. So in this case 1 by lambda, I will be writing this 1 by lambda dash, that is R 1 by 3 square minus 1 by 4 square. So this will be R 1 by 3 square, 1 by 9 minus 1 by 16, 16 minus 9, 7 divided by 16 multiplied by 9. So what is lambda dash we are getting? The lambda dash that we are getting here 16 into 9 divided by 7R. And what is lambda? 36 divided by 5R. Even if I divide this, so lambda dash by lambda will be getting this. So lambda dash by lambda, this is 16 by 9, 16 multiplied by 9 divided by 7R into 5R divided by 36. So this R and this R getting cancelled. So this is 9 1 ja, this is 9 4 ja, this is 4 1 ja, this is 4 4 ja. 4 into 5, 4 into 5, we are getting 20. 20 by 7 we are getting, okay? 20 by 7, that is lambda dash by lambda. So what is lambda dash? 20 by 7 into lambda. Answer is option C. Okay, answer is option C. An electron in hydrogen atom makes a transition n1 to n2, where n1 and n2 are the principal quantum numbers of the two states. So assuming the Bohr model to be valid, the time period of the electrons in the initial state is 8 times. It is going from n1 to n2. So time period t1 is how many times? 8 times time period in t2, right? 8 times of t2. So I told you t is proportional to what? N cube by z square. Anyway, hydrogen atom is there, so z equals to 1. So from here we can write time is proportional to what? N cube. So this t1 by t2 is equals to n1 by n2 whole cube. What is t1 by t2? From here t1 by t2 ratio is 8. 8 equals to n1 by n2 whole cube. Okay, n1 by n2 whole cube. So this, what is n1 by n2? And the n1 by n2 we have, that is 2 raised to 1. So n1 by n2 is 2 raised to 1. Which option we have 2 raised to 1? n1 equals to 4 and n2 equals to 2. Answer is option D. So there, here we have 2 raised to 1, that is n1 by n2 is 2 raised to 1. Answer is option D over here. So moving to next question. The question is coming from number of spectral lines formula. So let's, you note down the formula first. That is n1 to jumping to n2. If an electron is jumping from n1 to n2, the number of spectral line is given by, n2 minus n1 into n2 minus n1 plus 1 divided by 2. These are the number of spectral lines. For example, if let's, this is n equals to 4 and this is jumping to n equals to 1. One spectral line we can assume when it is jumping from 4 to 1, 4 to 2, 4 to 3. Next 3 to 1, 3 to 2 and 2 to 1, 1 2 3, 1 2 3, right? So it is jumping from where n equals to 4 jumping to n equals to 1. So number of spectral line will be given by 4 multiplied by 4 minus, where it is jumping to 1. So this is 4 minus 1 into 4 minus 1 plus 1 divided by 2. What we got? N equals to, this we got 3 into this side 4 divided by 2, we got 6. Okay, this is what we got, 6. I just taken the example over here. Now what is happening in this particular question? Let's see. Hydrogen atom in ground state. Right now hydrogen atom is in ground state. So hydrogen atom is in ground state, that is n equals to 1. Electron is sitting over here. Okay, is excited by monochromatic radiation of wavelength this much. So we are giving this much of light. So what is delta E? So delta E that we are having, HC by lambda. Hc by lambda. So what is delta E? Hc. What is Hc? 12440 divided by lambda in angstrom, right? So lambda in angstrom. So if you solve this, so delta E that we have 12440 divided by lambda in angstrom. So in this case, the delta E that will be writing this 12440 divided by lambda. What is lambda? It is absorbing the light of 975. So after solving this, we are getting this roughly 12.7 electronic volt. Okay, so 12.7 electronic volt. So let's solve this now. This is n equals to 1, this is n equals to 2, this one is n equals to 3, and this one is n equals to 4. So here the energy is minus 13.6, here the energy is minus 3.4, here the energy is minus 1.51, and here the energy is minus 0.85 approximately. So when it is taking this much energy, electron is sitting over here, this will absorb this much energy. If it is absorbing this much energy, electron is over here, electron is sitting over here, that is n equals to 1. It will absorb the energy and it will reach this particular point. Why? Because difference. What is difference here? You have to remember this difference. Difference in energy is how much? This one is 10.2 electronic volt. What is difference in energy over here? This will be, we're getting this 10.2, and this will be given by 1.5, and this is 1.5, and this is 13.6, this is 12.1, and this difference that will be getting here 12.75. So basically, where electron is absorbing this 12.7 electronic volt and is jumping from n equals to 1 to n equals to 4. Now from here the electrons will be coming back. So electron is coming back from the 4. The number of spectral lines they are asking from the 4. Okay, the number of spectral lines they are asking from the 4, because the difference energy is 12.7. So this energy is 10.2. This total energy, that is n equals to 1 to n equals to 2, that 3. The energy difference is 12.1. The energy difference with that is n equals to 1 to n equals to 4. That energy difference is 12.75. So in that case, we'll be writing what is delta E. The delta E will be writing this 12.75. This is giving electrons energy to move from n equals to 1 to n equals to 4. Now electron has reached now n equals to 4. It will be jumping from 4 to 4. It is jumping from 4 to 1 now. Maximum it can jump from 4 to 1. So in that case, number of spectral lines is given by, just now we calculated, 4 minus 3 into 4 minus 3 plus 1 divided by 2. Answer is of, sir, see, what we have taken the example, the same answer we are getting over here. I hope this is clear to everyone. That is number of spectral lines. You can note down this formula. In chemistry also you might have discussed this number of spectral lines when it is jumping from n1 to n2. Some energy levels of the molecules are shown in the figure with their wavelengths of the transition. So here we can check it. So when this type of question is coming, one thing is very much sure, that this much energy level, we have to add the energy level. Let's say this is delta E1 and this one is delta E2. So what is delta E1? What is delta E1? Difference in this energy and this energy, 2E and 3E. What is difference in this energy? Just a second. So electron is jumping from the different orbits over here. So one thing that you should keep in mind, if the electron is jumping from this point to this point over here, that is 2E to 4E. 2E to 4E. Can we written like this? Okay, so this lambda 3 will be writing this Hc by lambda 3 equals to difference in the energy from 2E to 4E. If I talk about the mod of this, that is given by 2E minus 4E. How much? 2E. Next, it is jumping from here to here. That is this point. What is energy? Minus 5E by 2, and this is minus 4E. Hc by lambda 1. What is Hc by lambda 1? Mod of this is given by this one, that is minus 5E by 2, minus 5E by 2, minus 4E. So this difference. Okay, next is Hc by lambda 2 also you calculate. What is Hc by lambda 2? So Hc by lambda 2, we are getting this. Here energy is minus 2E and here energy is minus 3E. So minus 2E minus 3E. So from here we are getting certain relation, that is Hc by lambda 1. If I talk about the mod of this, we are getting how much? 2E. Next, Hc by lambda 2, we are getting E. Hc by lambda 2, we are getting E. Next, Hc by lambda 3, sorry, this is lambda 3, this is lambda 1, this is lambda 3 and this one is lambda 1. This one, what we are getting? This relation we are getting here, this is 2.5, this is 4, this is 1.5E. okay, 1.5 e. So from here if I compare this one and this one, okay, so what is lambda 3? The lambda 3 is I can write here, if I compare this one and this one, the lambda 3 or lambda 2 is double of this. What is lambda 3? hc by 2e. And what is lambda 2? hc by e. And what is lambda 1? hc by 1.5 e. So if I compare this, I can write here lambda 2 is double of lambda 3, yes or no? Okay. And if I compare this one and this one, which one is bigger? The lambda 1 is bigger. The lambda 1 is greater than lambda 3. So we are coming to this conclusion, lambda 1 is greater than lambda 3. So lambda 1 is greater than lambda 3. Any option is there? Lambda 1 is greater than lambda 3. And second option we have, what is that? Lambda 2 is twice of lambda 3. Lambda 2 is twice of lambda 3. Lambda 2 is twice of lambda 3. Yes, correct. Lambda 2 is twice of lambda 3. Okay. Two options are there. This one is wrong. So lambda 2 is twice of lambda 3. So let's check one. This one, lambda 2 is twice of lambda 3. And what about lambda 1 and lambda 2? Which one is bigger? Lambda 1 and lambda 2. So lambda 2 is bigger than lambda 1. Okay, lambda 2 is bigger than lambda 1 and lambda 2 is twice of lambda 3. Answer is option D. Right. So next our topic is that nucleus. What is nucleus? In the nucleus we have, this will be Z and this side we have A. So this is what we define mass number and this is what we define. This is what we define atomic number. This is what we define mass number. The mass together inside the nucleus there will be protons and there will be protons and there will be neutrons. So if I am writing here Z and A, so this is having Z number of protons and this having A minus Z number of neutrons. So here we will be writing Z protons and A minus Z neutrons. Okay, together that protons and neutrons we togetherly call it as nucleons. Atomic numbers, total number of protons in given nucleus is what we define atomic number. And what is mass number? Sum of the number of the total number of the neutrons and protons, we call it as mass number. A is the mass number we have. So if we talk about the nuclear size, what is nuclear size? The radius of the nucleus is directly proportional to a ki power 1 by 3. The radius is proportional to this a naught a ki power this I'll be writing this r equals to r naught a ki power 1 by 3. What is a here? Mass number. And what is r naught value? That is 1.1 into 10 ki power minus 15. So that is radius is given by this. If we talk about the volume, what is the volume? Volume is proportional to volume is equals to 4 by 3 pi r cube. So volume is 4 by 3 pi r cube. So volume is proportional to r ki power cube. Okay. So r ki power cube means volume is proportional to mass number over here. If we talk about the mass of nucleus, what is mass of nucleus? That is density multiplied by volume. Okay. So mass of the nucleus is, let's say, m. What is total mass? We'll be writing this. Total mass will be A multiplied by mass of 1 proton. This is the total mass of the nucleus is equals to rho into volume. What is volume? 4 by 3 pi r cube. And I told you volume is proportional to this A. Volume is proportional to r cube. And what is this? I can write here. The volume is proportional to r cube. So volume V is equals to 4 by 3 pi r cube. So in that case, so if I talk about the nuclear density, what is nuclear density? A into mass of the proton divided by 4 by 3 pi r cube. Okay, A into 4 by 3 pi r cube. So this one is A into mass of the proton divided by this. What is r cube? 4 by 3 pi. What is r? R naught into a ki power 1 by 3. So this is r naught cube into A. So this A or A cancel. This particular term, that is mass of the proton, and this is the constant. So this nuclear density is constant for element. Hydrogen, helium, lithium, beryllium, boron, carbon. All the elements will be having approximately same order of nuclear density, and that is given by 10 ki power 7 kg per meter cube. But the radius of the each element will depends on its mass number. That is radius is proportional to a ki power 1 by 3. Volume is proportional to volume is proportional to r. The volume is proportional to a ki power 1. Nuclear density will be same for everywhere. Next we have nuclear force. Inside the nucleus, what actually happens is that inside the nucleus we will be having protons and we will be having neutrons. So it is not that much feasible to hold the protons together, they are repelled by the Coulombic force of the repulsion, right? The repulsion is very high inside the nucleus, that they are pushing each other, but still the nucleus is very stable because of this governing one force that we define strong nuclear force. And a strong nuclear force is a force that will be acting between two protons, between one neutron and proton, between two neutrons. It does not do any differentiation between whether you are having charge or not. So this one is independent of the charge. It is non-central force, does not act center to the center. It is very short range force. What is it? Is very short range force that we should keep in mind. It is very short range force. One force that is exist between the two protons, between any two nucleons inside the nucleus. That force is what we define a strong nuclear force, a strongest force in the nature. But the only drawback is that it is very short range force. Short range means if the order of the two nucleons should be in the order of 10 to the power minus 15 meter. If they are separated by 10 to the power minus 15 meter, then only force will be acting. That is this particular force, nuclear forces. A strongest force in nature, yes. This will be strongest force in nature. Very short range force, attractive forces there. It is 100 times greater than that of electrostatic force and 10 to the power 38 times greater than that of gravitational force. So these are the properties we have for the nuclear force. And if we talk about the mass defect, so what is mass defect? Suppose if I write alpha particle, suppose if I write helium nucleus. Helium nucleus, what is helium nucleus? It is having two protons plus two neutrons. Two protons plus two neutrons. Helium nucleus is two protons plus two neutrons, right? So suppose if I give two protons plus two neutrons, and from that we are combining and forming one helium atom, helium nucleus, two protons and two neutrons. So ideally what should actually happen is that, ideally what it should happen is that the proton and neutron. So sum of the mass of the two protons and neutrons should be equal to mass of the nucleus, but this does not happen. Ideally this should have been happened, but this does not happen. Means sum of the masses of the protons and sum of the masses of the neutrons should be equal to mass of the nucleus, because inside the nucleus we have the proton and neutrons, but this does not happen. Why? Because some part of the mass is not there. So mass of the nucleus, remember this, mass of the nucleus is always less than sum of the mass of the all the nucleons. That difference is what we define sum of the mass of the nucleons. That difference is what we define. That difference is what we define. That difference is what we define mass defect here. So difference in the sum of the mass of the nucleons and mass of the nucleus is what we define mass defect. Where this mass is going, that mass is converted into binding energy. What is binding energy? The binding energy is the energy which is binding the given proton and neutron inside the nucleus, we can say. Or suppose if I give the helium atom, if I break the helium atom into protons and neutrons, this much energy is required to break the nucleus, binding energy. So here we define mass defect. The mass defect is, I will be writing this ZMP plus A minus Z into Mn. So what is this term? Z into MP, that is sum of the mass of the protons plus sum of the mass of the neutrons minus mass of the nucleus. This is what mass defect over here. And what is binding energy from the energy mass equivalence? That is delta M into C square. So we have that relation, that delta M into C square. So if delta M is equals to 1 atomic mass unit, then delta M into C square equals to 931.5 mega electronic volt. So if 1 atomic mass unit is equivalent energy of using this mass energy equivalence, that is 1 atomic mass unit is having energy of this one, that is 931.5 mega electronic volt. This particular thing that you have to remember, that is 1 AMU in equivalent energy is 931.5 mega electronic volt. So this is the thing that we should keep in mind. Okay. So again, the binding energy is delta M into C square. Whatever the extra mass that is getting, whatever the mass that is getting difference. So we are taking two neutrons, we are taking two protons, and we are combining, forming the helium nucleus. The mass of the helium nucleus is less than sum of the mass of the nucleons, and that difference in the mass is converted into binding energy. The binding energy is the energy which is required to hold the protons and neutrons inside the nucleus, and this energy will be released when two protons and two neutrons will combine to form the helium nucleus, and this energy will be required to break the helium nucleus into constituent nucleons, that is the protons as well as neutrons. I think this is clear to everyone, right? So energy will be released and energy will be absorbed. One thing in chemistry also we might have discussed, like if energy is released during any chemical reaction, the reaction is more feasible and the product is more stable. If the energy is absorbed during chemical reaction, then reaction is less visible and the product is less stable. So here we define some of the terms that we define Q value of the reaction. What is Q value of the reaction? Suppose if it is going from A to B, any nuclear reaction happening from A to B. So here, well, we define that is Q value of reaction, energy release or energy absorbed. So Q value is defined as binding energy of the product minus binding energy of the reactant. So product binding energy minus reactant binding, that is a Q value. Again, so different scenario with this first case, that is when energy is released. When the energy is released, the product is more stable. The binding energy of the product will be more as compared to reactant. So in this case, the binding energy of the product is more than binding energy of the reactant. So if energy is releasing, means we are getting the energy from the nuclear reaction. So product is more stable and this condition is satisfied. The binding energy of the product minus binding energy of reactant. Second, when the energy is absorbed, whenever the energy is absorbed, so when the energy is absorbed, the product is less stable and the binding energy of the product is less than binding energy of the reactant. More is the binding energy, more stable the nuclei will be. So here the binding energy of the reactant minus product, that will be writing in this particular case. And there is one more formula that we can write here. Q is equals to mass of reactant minus mass of product into C square. So this is also one formula and this is also one formula that will be useful in solving the numerical problems from here, from the binding energy we have. So this particular graph tells about the binding energy per nucleon. So binding energy per nucleon, what is the meaning of this? Binding energy divided by mass number is what we define binding energy per nucleon. For example, this iron is having maximum binding energy per electron. So binding energy per nucleon of iron is how much? 8.75 mega electronic volt. So what is binding energy of the iron of one atom? What is mass number of this atom? This one is 56. So this one will be writing this 56. So per nucleon, the binding energy per nucleon is 56. This I will be writing this 8.75. So what is binding energy of the nucleus? One nucleus of this Fe is given by, just multiply this 56 into 8.75. So if you plot the graph of this, that is graph of binding energy per nucleon versus the mass number, if you are plotting this, in this case, what you have to focus here is that the one which is having higher value of binding energy per nucleon is more stable nuclei in this group. So which one is more stable? That is Fe. That is highest value is how much? 8.75 mega electronic volt. 8.75 mega electron volts. Iron is the most stable nuclei in the universe, we can say, for example, till now what we discovered. Second, so initially the binding energy per nucleon value is less for small lighter nuclei, and this side again the binding energy per nucleon value is less for this heavier nuclei. This particular reason where we are getting this particular reason, when the mass number is in this particular range, mass number is this range, A is less than 170 and greater than 30. This is what we define stable nuclei. Okay, this is what we define stable nuclei when the mass number is less than, because this is having a higher value of the binding energy per nucleon. And this side, when the A is less than 30, this is unstable, little bit relatively less stable. And this side, when the A is greater than 170, this also less stable. So what actually happens that this nuclei together, they will be joining and forming one bigger nuclei so that they can come under stable. Everyone wants to achieve this stability like that. These two nuclei will forming and joining together, and they will increase their mass number, and they will be forming this particular process. When the lighter nuclei, the less mass number wala nuclei will join to form heavier mass number to achieve the stable to in this particular range. This particular process is what we define fusion. Fusion is increasing the mass number. On the other side, when the mass number is more than 170, some radioactive element, that is heavier nuclei, itself will break into two parts which will fall under this stable nuclei. So this particular process in which the bigger nuclei will break itself into lighter nuclei, this process is what we define fission, nuclear fission. So this is nuclear fusion, and this is nuclear fission, right? This nuclear fission. So this process happens to achieve this stability, and this particular elements that is sitting between this 30 and 170 range, that is the most stable nuclei. So one thing is very much clear from this graph: the higher the binding energy per nucleon, is the more value of the more stable nuclei we have. So let's say solving some of the questions. Just one more topic left, that is alpha decay. So what is alpha decay? I will be writing this alpha decay. So if any element X is there, an alpha particle is, X is there, and this is atomic number Z and mass number A. Sorry. So atomic number Z and mass number A. If this particular element is removing the alpha particle, then let's say this is becoming daughter nuclei. So Z is reduced by how many times? Z minus 2, and mass number decreases by 4 because alpha particle is coming, and plus some amount of energy will be released. So this process is what we define alpha particle. Alpha decay we call it as, and this alpha particle, because Z is atomic number decreases by 1, decreases by 2. Atomic number decreases by 2, mass number increases by 1. Mass number increases by 1, by 4. Okay, mass number increases by 4. In which case, alpha particle is removed because alpha particle is helium nucleus. You can check some of the atomic number on the left hand side of the equation should be equal to atomic number on the right hand side, and the same goes for the mass number also. So this one is A, this one is A minus 4, this will be 4. So next we have this beta minus decay. So what is beta minus decay? If any element is going X, this one is A and this one is Z. Beta minus decay. So beta minus decay means removal of one electron. So in this case, what will happen? This will become Y. Atomic, I have written this. This will be Z and this will be A. Atomic number increases by 1. Mass number will remain same. Plus electron minus 1, and this will be 0. And this is along with the release of this anti-neutrino particle. And this is the not electron which is rolling around the nucleus, but this electron is coming from the nucleus. That electron is what we define beta minus particle, or we also simply electron from the nucleus. And next we have this. What is that? Beta plus decay. So in beta plus decay, what actually happens? X, Z, A. So here this will become Y. Atomic number decreases by 1, mass number remains same, plus release on one positron. Positron is antiparticle of electron. So this is positron, just opposite of that of electron. Mass will be 0, and what is this? Along with the release of neutrino. So this will be neutrino. So when it is actually particle, we are getting antiparticle of neutrino. This side, when it is antiparticle, we are getting particle of the neutrino. So this is the beta plus decay. So these are the things that you should keep in mind. Mass number remains same. In beta minus decay, atomic number increases by 1. In beta plus decay, it is atomic number decreases by 1. These are the 3 ready to decay that we should keep in mind. A nucleus of mass number 189 splits into 2 nuclei. So X 189 is split into 2 nuclei having mass number. So this will be Y 125 plus Z 64. The ratio of the radius of these 2 daughter nuclei. So what is radius is proportional to A power 1 by 3. So that's it. So this R1 by R2 is equals to A1 by A2 all to the power 1 by 3. So that's it. We are getting how much? 125 by 64 to the power 1 by 3. So 125 to the power 1 by 3, 5 by 4. Answer is 5 raised to 4. Moving next. The 2 nucleus have the same mass number in the ratio. The ratio of the nuclear densities. I told you nuclear density is 10 to the power 17 kg per meter cube. That is constant for a given material. That does not depend on the mass number. So answer will be 1 raised to 1. Mn and Mp represent the mass of the neutron and proton respectively. An electron having the mass m has the n neutrons and z protons. The correct relation will be given by Mn is the mass of the neutrons. I told you the mass of the nucleus will always be less than sum of the mass of the protons plus sum of the mass of the neutrons. How many neutrons we have? N neutrons. So n into Mn. So this particular, that is m, will be less than sum of this. This is the mass defect. The difference is what we define mass defect. So this is the sum of the mass of the protons and neutrons. This will be more than always the mass of the nucleus, right? This one, if m a z, this is the mass of the nucleus and this is the mass of the proton, this mass of the neutron we have. Then what they're asking? Binding energy. What is binding energy we have? The binding energy I told you, that is delta m into c square, right? Delta m into c square. So this binding energy is by c square equals to delta m. Okay, what is they asking? Mass of the nucleus they're asking, right? So in this case, I'll be writing this. What is delta m? What is delta m? The mass sum of the mass of the protons, that is Z into Mp, plus sum of the mass of the neutrons, A minus Z into Mn. This is the sum of the mass of the nucleons minus mass of the nucleus. So this, from the mass of the nucleus we can write. And what is delta M? Binding energy by C square. So this is binding energy divided by C square is equals to this Z into Mp plus A minus Z into Mn minus mass of the nucleus. What is mass of the nucleus? From here we can write, that term will go this side. So Z into Mp plus A minus Z into Mn minus binding energy divided by C square. Answer is option C. So mass of the nucleus is given by, this is the sum of the mass of the nucleons and this is mass defect. Sum of the mass of the nucleons minus mass defect is equals to mass of the nucleus. A nucleus with mass number 240 breaks into two fragments, each of mass number 120. Binding energy per nucleon is given by, so this mass number x 240, it's break into 2 times of this mass number, what is that, 120. The binding energy per nucleon of the this one is 7.6 mega electronic volt, while the fragment is 8.5 mega electronic volt. So this one is having 8.5 mega electronic volt, and this one is unfragmented. That is unfragmented is unfragmented. Sorry, this one is fragmented. Unfragmented means which have not been broken. So this one is, while there are fragment, this one is having 7.6 mega electronic volt. Okay, so what is binding? What is Q value of the reaction? The total gain in binding energy of the process. So what is binding energy of the product? I'll be writing this. Binding energy of product is 2 multiplied by, because 2 atoms is there, multiply by 120, because this is what binding energy per nucleon. This is binding energy per nucleon. So I have to multiply with 120, multiply how much? 8.5 mega electronic volt. And what is binding energy of the reactant? So what is binding of the reactant? This is only single atom is there, multiply with 7.6 multiply by 240. So we have to just multiply with mass number. This is 7.6. So what is this difference? Delta in binding energy difference, we are getting this. This is 240 multiply by this 8.5 minus 7.6. Approximately we will getting this 240 into this one is 0.9. So 240 into 0.9. So approximately we will be getting this 216 mega electronic volt. The binding energy per nucleon in the deuterium and helium nuclei are in the ratio 1.1 mega electronic volt. Deuterium, so H12. When the two deuterium nuclei fuse to form one helium nucleus, again H12, they are forming what? Helium nucleus, He24. The energy release in this reaction will be given by. Okay, fine. So what is binding energy of product? So how many nucleus we have? 2. Multiply by this. This one what is what they given. This is for the binding energy per nucleon for deuterium is 1.1 and for helium is 7. So 7 multiplied by how much mass number we have to do? So 2 into 4 into 7. This is the binding energy product. So for one helium nucleus we have 7.0 mega electronic volt per nucleon. We have to multiply with 4, multiply by 2. What is binding energy of reactant? The binding energy of reactant is given by, again 2 times of this, 2 times of this is 1.1. So this is 2 multiplied by this. Why again 2? Because mass number is 2 here, 2 into 1.1. So this we are getting the relation. That difference what we have to write. Q value is the binding energy of product minus binding energy of reactant. So binding energy of the product minus binding energy of the reactant. Okay, so this for 56 minus this one 4.4. Okay. Okay, we are not getting 2 times. Sorry. We are not getting 2 times of this. We are getting only single time. So this will be 4 into 7. 4 into 7. So this one is 28 minus 4.4. So this will be 23.6 mega electronic volt. Approximately 23.6 mega electronic volt. In the given nuclear reaction, we have the element X is 1122 NaX plus positron they have mentioned over here, plus this one is neutrino. So what they are asking, what is element X is given by? Simple thing is there. You write this one Na, this one is 11, this one is 22, this is going to X, and this one is E plus 1 we are getting, so E plus 1 I will be writing on the downward side. This one is positron and this one is plus neutrino, and this particular term they are asking what is this particular term over here. Now check the mass number. This is 22, this one is A, and let's say this one is Z. So 22 should be equals to A plus 0. This does not have anything, right? This does not have anything. So this next 11 should be equals to Z plus 1. So what is Z value? Z value is 10. And what is A value? A value is 22. Z value is 10, A value is 22. Z value is 10, A value is 22. Answer is option C. Okay, answer is option C. A certain mass of hydrogen is changes to helium by process of fusion. The mass defect in the fusion reaction is 0.02866. The energy liberated. How much energy is liberated? E is equals to delta M into C square. I told you what is delta M value? 0.02866. If you convert into this, we have to multiply this 931.5 mega electronic volt. So we have to do this approximately. I am writing this. This is 0.03 multiplied by 931.5. So approximately 9 into 3 we are getting 27 point something, that is 26.7 mega electronic volt we are getting from here. So this particular question, so here we have the series of expression in the nuclear emission stated above. The mass number and the atomic mass number of Q respectively will be given by, okay fine. So X 82 290, alpha particle is released, so this will become Y. What is Y? 82 minus 2. I told alpha particle is released from here. Alpha particle release means atomic number will decrease by 2, mass number will decrease by 4. So this is 286. Next it will become positron is released. When the positron is released, so what will happen in this case? When the positron is released, so I will be writing this. So when the positron is released, this will become Z. Atomic number will decrease by 1 and mass number will remain same, 286. Next we have this one, beta minus particle is released. When the beta minus particle is released, positron means this is beta plus emission. So in this case atomic number will increase by 1, 79 plus 1, that is, and this will remain 286. Last one, electron is released from here. So what is they asking? Product Q, no? Okay. So again electron is released, so this will become, electron is released, this will become 81 and this will be remain same, that is 286. Okay, 286. So mass number will increase by 1. So this will be writing, answer is option D, 286, 81. Okay, so last question of this, radioactive elements decays. So here X, Z, A. This has become B, Z minus 1. Okay. Next, this will be C, Z minus 3. This will become D, Z minus 2. Okay, they are not mentioned anything about the mass number. Okay, let's say we can solve this or not. So how we can solve this particular expression? This is atomic number decreases by 1. So this has to be beta minus beta plus decay. Beta plus decay. Okay. Next, after that atomic number decreases by 2. This is minus 2. This is minus 1. Atomic number decreases by minus 1. A beta plus decay happens during this. So this is alpha particle and this is again atomic number increases by 1. So this is beta plus and alpha and beta minus decay. So these are the topics that we have discussed so far that in today's, that is atoms and nuclei. On the Monday session we'll be discussing the electronic devices. So in this case, what is the important thing? The theory of the semiconductor, we have P type, N type, extrinsic semiconductor, PN junction diode, forward biasing and reverse biasing. Then we have application of the PN junction diode. It is used as LED, rectifier, photodiode, solar cell. Then we have the logic gates. We can expect 2 to 3 questions from this. So definitely attend this particular chapter on that day. Till now, practice well and revise thoroughly and revise all the formula and all the concept. Till now, we see all of you on Monday.